Hello, welcome to ISAT431 Advanced Manufacturing Processes and Systems. This is lecture 2 in additive manufacturing. Today, we're going to talk about different additive manufacturing processes. So you can see there are multiple processes in 3D printing. We're going to go through them one by one. The first process is also a very common process we see, in our lives. It's called fused deposition modeling. So fused deposition modeling, especially when we are looking at the polymer materials. For example, in our library, in our lab, you see this. It has a spool of filament, and then filament will go through a nozzle, and then will be heated by the nozzle, and then material will be deposited from the nozzle to a bed. Then layer by layer, it will start to create the material, create the part. So this is the typical process for fused deposition modeling. First, let's look at this. Watch this video.
Fused deposition modeling, or FDM, is a layer additive manufacturing process that uses production-grade thermoplastic materials to produce both prototype and end-use parts. This technology is known to accurately produce feature details and has an excellent strength-to-weight ratio. FDM is ideal for concept models, functional prototypes, manufacturing aids, and low-volume end-use parts. The FDM process begins by slicing 3D CAD data into layers. The data is then transferred to a machine, which constructs the part layer by layer upon a build platform. Thin thread-like spools of thermoplastic and support material are used to create each cross-section of the part. Similar to a hot melt glue gun, uncoiled material is slowly extruded through dual-heated nozzles. The extrusion nozzles precisely lay down both support and thermoplastic material upon the preceding layers. The extrusion nozzle continues to move in a horizontal XY plane while the build platform moves down, building the part layer by layer. The finished part is removed from the build platform and cleaned of its support material. Raw FDM parts have visible layer lines. However, service providers such as Solid Concepts offer multiple finishing options to create smooth, even surface parts, including hand sanding, assembly, and cosmetic paint. Since FDM parts are constructed with production-grade thermoplastics, including ABS, polycarbonate, and Ultem, they are both functional and durable. FDM is utilized in a number of industries, including aerospace, automotive, industrial, commercial, and medical.
All right, so that's an introduction about fused deposition modeling. So when we're looking at this, we want to pay attention to the material, which is thermoplastic materials. As we talk about in ISAT430, thermoplastic material versus thermosetting elastomers, that they can after the melt they can actually return back to its they can be formed with its shape. So that's why only thermoplastic material can be used when you are we are using this fused deposition modeling with polymers. And some of the mechanical property factors include the layer thickness. When you are printing a part, sometimes you might notice there are very clear lines about those layers of the filaments, and this is very typical in fused deposition modeling because the nozzle is depositing materials layer by layer. However, you can you can control the settings by best said, the layer thickness is a little bit smaller. However, sometimes you can still see the layers just because of the nature of the material of the process. And also it also depends on the filament material as well, the width of the filament, the orientation of the filament, and also the gaps, air gaps, in between of those. Something you might notice that when we are 3D printing or use this diffuse deposition modeling, you can see the structures inside. There can be different structures. Either it can be solid materials that without any kind of gaps, or it can be with certain patterns, right? Either honeycomb or some other patterns. For example, I have a research study on designing some kind of bioinspired structures for 3D printing. So instead of those kind of muscle structures, maybe you can create some other structures that can support the inside of the material, inside of the shape. And also in 3D printing, when you are doing FDM, you can also select different patterns inside of the product when you print. And the weakness is still it's an interlayer distortion. So because when the materials start to bond each other, right, fuse each other, and because of the heat, it might create a little bit distortion, between the layers. So that's some kind of a little bit of weakness with this process. But the best part is it's low cost and it's fairly simple process, right? And also it prints a little bit fast as well, compared to some other process that might take days, many days, right? With the same part. Drawbacks we mentioned it before, layer by layer appearance, poor surface quality, as you can see from those pictures. Limited number of thermoplastic materials. We're gonna talk about it in next week's class about the material in 3D printing. But for polymers, we the very limited material we can select actually for FDM. Also, sometimes we have fiber reinforced composites as filament materials, and they can also strengthen the mechanical properties of the part. So this is the fuse deposition modeling. Next one is the powder bed fusion processes. So powder bed fusion processes, this is a group of processes that typically use either a laser or electron beam. So idea is we're gonna lay all the powders, fine powders on the platform, and then we're gonna use a laser or basically an energy source, right, to fuse the particles with different layers, and then we're gonna start to create the pattern of the product. So and then we're gonna put another layer of the powders, and then do it again, and then put another layer and do it again. So this is how we create 3D print parts with powder bed fusion processes. There are multiple processes. We're gonna go through each of the video with you, and direct laser metal laser sintering, the selective laser melting, and selective laser sintering. So this is SLM, this is SLS we typically see, and this is the EBM we typically see, and these processes are kind of similar. For EBM we use electron beam, for others they use lasers, but when they melt, the powder is a little bit different. For example, selective laser melting is fully melted and it's fused together, while selective laser sintering, it does not fully melt the powder. It just need to center the powder at two different layers, and then that's good enough. So there are some of the differences in those processes. Then now let's look at each one of those.
Direct metal laser sintering, also known as DMLS, is an additive manufacturing technology that creates metal parts directly from 3D CAD data without the need for tooling. DMLS utilizes a variety of metal and alloy materials, such as stainless steel, cobalt chrome, and Inconel, to create strong, durable parts and prototypes. DMLS is an excellent choice for functional metal prototypes, high-temperature applications, and end-use parts. The DMLS process begins in the same fashion as other layer additive manufacturing technologies. A program takes 3D CAD data and mathematically slices it into 2D cross-sections. Each of these sections will act as a blueprint, telling the DMLS machine exactly where to sinter the metal material. The data is then transferred to the DMLS equipment. A recoater assembly pushes powdered metal material from the powder supply to create a uniform layer over the base plate. A laser then draws a 2D cross-section on the surface of the build material, heating and fusing the material. Once a single layer is complete, the base plate is lowered just enough to make room for the next layer. More material is raised from the cartridge and recoated evenly on the previously sintered layer. The DMLS machine continues to sinter layer upon layer, building from the bottom up. As the part is built, support structures are added to give supplemental strength, fine features, and overhanging surfaces. The completed part is then removed from the base plate and treated with an age-hardening heat process to further harden the part. Any support structures are also removed at this time. With numerous surface treatment and hand polishing options available through service providers, DMLS parts can be used in highly cosmetic applications. Typical uses for DMLS include tools and manufacturing aids, small integrated structures, dental components, surgical implants, and aerospace parts.
Then the next process is electron beam melting, EBM. This is a titanium alloy material. So titanium material is biocompatible, so we have been always used a lot in biomedical medical care. For example, some implants. All right, next is selective laser melting. that's the laser. Alright, so this is selective laser melting compared to SLM selective laser sintering. It does not fully melt the particle. So the energy intensity for that is a little bit lower than the selective laser melting. So that's why selective laser melting can make some of the products that with high that requires high energy intensity, like steel, aluminum, those kind of metals. While selective laser sintering, instead it can actually make some other like polymers or some of the light metals and also alloy powders.
Selective laser sintering, or SLS, is a rapid prototyping technology that turns 3D CAD data into physical parts in a matter of hours. SLS is an additive manufacturing technology that uses powdered nylon 11, nylon 12, and PEEK materials. Parts produced are lightweight, highly durable, and both heat and chemical resistant, making SLS an excellent choice for producing production parts without the expense of tooling. The SLS process begins by splitting 3D CAD data into thin cross-sections or layers. The data is then transferred to the SLS additive manufacturing equipment. The machine then begins to create the first layer. After a leveling roller spreads a thin layer of powdered material across the powder bed, a CO2 laser traces the cross-section on the material. As the laser scans the surface, material is heated and fused together. Once a single layer is complete, the powder bed is lowered to make room for the next layer. More material is introduced from the powder cartridge and rolled out smooth, while unused material is recycled. The process is repeated, building layer upon layer until the part is complete. As SLS parts are built, they are encompassed by unsintered powder, which provides supplemental strength and eliminates the need for support structures. Complex designs and assemblies, once thought impossible, are now being redesigned with SLS as cost-effective integrated structures. Solid Concepts manufactures parts utilizing nylon with property-enhancing fillers to create rugged SLS parts suitable for a variety of prototype and production applications. Typical uses for SLS include tools and fixtures, fuel tanks, flight-rated components for unmanned aerial vehicles, automotive designs, air ducts, architectural models, and artistic sculptures.
All right, so that's about powder bed confusion processes. There are many processes, and some typical factor that affect the quality is the powder raw material, which is the powder particle size, the shape, the packing factor, all those typical powder metallurgy characteristics, and it gonna affect the quality of the melting or sintering as well. So that's why in powder bed fusion processes, you also need to have a very good control of the raw material, as well as the energy source quality. Advantage with those processes is that it has very good resolution, good quality of printing compared to some other processes like fused deposition modeling and it can make very complex structures with 3D printing. And a lot of applications are actually used in aerospace, electronics, and also in medical care, like tissue engineering, lattices, all those things. And some of the drawback will be the process, of course, is very slow. It's very typical to most of the 3D printing processes, and high cost because of the equipment are so expensive. A lot of time is $1 million or more than $1 million for a process. It also depends on the workspace volume, how much is the workspace, and you can tell from the videos that a lot of those parts are very, very small parts. If you want to make bigger one, you will probably need bigger laser intensity as well, and those kind of equipment are typically very, very high cost and also maintenance. Another thing is it's a safety about these processes. Metal powders are explosive, so some of the metal powders can pose very dangerous hazards to the human being. For example, metal powder can be in the air as well. When you're handling metal powder, some of the powder will come into the air, and then when you breathe, they might affect your inhalation. So that's also something you want to take care of when you are dealing with those metal powders and these 3D printing processes. Also, when you are making those products, there's a high porosity because they are powders. So the powders and the particles, when they fuse, always there's a little bit of gap in there. For some of the products, it might be good with high porosity. For example, with some of the tissues, some of the bones, it's good to have those because natural bone structure can actually be infused into the implant. But for a lot of other products, having porosity might not be a good thing. Another process is inkjet printing. So this is also one of the main methods in additive manufacturing. It can also make ceramics as well. So inkjet printing, from its name, you can tell it's kind of inject. So it's depositing droplets. Droplets from a nozzle, and the droplets can be it can be polymers, it can be ceramics, or it can liquid metals as well. So those some droplets will form a pattern on the platform, and then will solidify when you remove that the part source. So this is inkjet printing.
HP's multi-jet fusion technology produces quality, functional parts at a production speed which is up to 10 times faster than today's competing products. Unlike the slow point processes of some current technologies, HP's multi-jet fusion technology processes parts in 2 fast, area-wide passes to achieve top-speed part production. The process begins by applying a layer of material in a work area. In the opposite direction, in one continuous pass, we print fusing and detailing agents across the full working area. This pass combines the printing with the fusing energy, and the process is then completed. HP's proprietary architecture is capable of printing 30 million drops per second along every single inch of bed width, enabling extreme precision and dimensional accuracy. To produce truly functional parts, it's important to ensure that the material has been properly fused and that part edges are smooth and well-defined. To achieve part quality at speed, HP invented a multi-agent printing process. In this process, a fusing agent is applied on a material layer where the particles are meant to fuse together. A detailing agent is applied to modify fusing and create fine detail and smooth surfaces. The area is exposed to energy, and reactions between the agents and the material cause the material to selectively fuse together to form the part. The fusing process requires accurate temperature control across the entire material layer. HP Multi-Jet Fusion's closed-loop thermal control system does this by measuring temperatures at hundreds of points on the material bed. This information then determines which areas receive more energy to raise the temperature and which areas are cooled, allowing for control of thermal bleed and layer-to-layer fusing and cooling. The result is full control over mechanical properties, dimensional accuracy, and repeatability. The process is then repeated until a complete quality, truly functional part has been formed. This is how HP's proprietary area-wide processing compares with existing popular point processing technologies for building functional parts. In the time it takes these slower point processes to build 1,000 parts, HP's multi-jet fusion technology would have created several thousands of parts. Using HP's proprietary multi-agent printing, the HP multi-jet fusion technology achieves new levels of part quality at these breakthrough speeds. In 3D design and printing, a voxel represents a value on a regular grid in a three-dimensional space, like a pixel with volume. By controlling the properties of each individual voxel through agents, HP Multi-Jet Fusion can produce parts that can't be made by other methods. Taking advantage of HP's in-depth knowledge of color science, HP's 3D printers could in the future selectively print a different color at each volumetric pixel. A single 3D printed part could have literally millions of colors. But more than just full color printing of functional parts, HP's multi-agent system enables a fundamentally different approach that could unlock the full potential of 3D printing. At each voxel, HP transforming agents could control surface texture, wear, and friction, enabling single parts with multiple textures or the monitoring of part performance. The transforming agents could control the translucency of each voxel, enabling the printing of lenses or sensors. We could also optimize the strength and stiffness in portions of a part and print elastic voxels in other portions of the part. The conductivity of certain voxels could also be controlled, enabling embedded electronics. HP transforming agents could also be used to enable the printing of new advanced materials or enable emulating different materials at each voxel. HP's multi-jet fusion technology could enable design and manufacturing possibilities that surpass the limits of our imagination.
All right, so I think the video talks a lot about this process and some of the factors to determine the quality particle size distribution, viscosity of the ink and the solid content, and also the extrusion rate, the nozzle size, speed of printing. That are all common factors also affect most of the manufacturing 3D printing process. If you are dealing with metals or other materials. And some of the drawback is maintaining workability. It's a little bit hard, the coarse resolution, and also lack of adhesion between the layers. So these are the common drawbacks. And because of the inkjet printing, after you printed it, you drop you deposit the droplet there, and there's no other, it just solidified by itself, and there's just no other energy source that is to bound anything, right? So that's why there's the adhesion is a little bit weak in this process. Another process in additive manufacturing is the contour crafting, which is very similar to fused deposition modeling. Sometimes we hear examples of 3D printing a house or some bigger equipment or something, a structure. It's probably talk about contour crafting. Similar to the fused deposition modeling, it's also there's a feeding material, and the material goes through a nozzle and let itself solidify. It's a concrete structure, so you can print a house out of here if it's if you make the axes and workspace big enough. Some of the bold ideas is that they can actually make this print some of the building structures on the moon or on the Mars, and then let the robots on the machine to build a city or build something by itself. All right, we'll just stop here. And next process is the stereolithography. This is also the start of the 3D printing, where it started to use a resin in as a raw material, and then use the UV light or electron beam to initiate the reaction. So that reaction is the polymerization, right? Under UV light or electron beam, and an advantage with it is that this kind of process SLA provides very good fine resolution of the product as low as 10 microns, and it can be effectively used in nano composites. So because they can control the light and electron beam very precisely, and the material is there. It's unlike fused deposition modeling. Fused deposition modeling, you are depositing the materials layer by layer, and then sometimes there are distortions of the heat, thermal expansions of the materials. They can affect the accuracy as well. So that's why stereolithography might have a better resolution compared to other 3D printing processes. Of course, this process is very slow and very expensive. These are all the drawbacks. Same range of materials that you can select is also very limited.
Stereolithography apparatus, or SLA as it is commonly known, is the oldest of the rapid prototyping processes, originating in 1986.
Let me see if I can.
Under the 3D Systems Company in California. Here we have the Viper SI2 SLA system. It has a maximum build area the shape of a cube with equal 250mm sides in standard quality, or 125mm long and wide by 250mm tall in high resolution. The process begins with the creation of a 3D CAD model. This can be done in a variety of programs, including NX, SolidWorks, and many more. Once complete, the model is converted to an STL file and sent to the build station control software where support scaffolds are automatically added, and the part is cut into a series of slices around 0.003 of a millimetre in thickness. The model is now ready to be printed. The build platform is lowered into a vat of photocurable epoxy acrylate liquid resin, known as LV Grey, so that it rests 0.003 of a millimetre below the surface. An ultraviolet laser is directed onto the resin using a series of computer-controlled mirrors. The laser causes the material to polymerize. The laser itself has 100 milliwatts of power available to it and has a beam diameter of just 0.075 millimeters, meaning that the solidification process is very accurate. The build platform then lowers a single layer thickness. The leveling blade sweeps across to ensure that the new level is recoated with a layer of liquid resin. The laser then selectively solidifies the next layer. This process of recoat and scan is repeated layer by layer until the model is complete, and the platform then rises up and out of the resin to allow the unsolidified resin to drain away. Upon completion of the model, it must be removed from the machine and post-processing of the model must be performed. First, any excess liquid and support structure are removed. The part is cleaned using isopropyl alcohol to remove any uncured excess resin, and it is then cleaned using air and water to remove the solvent. The part is then placed in an ultraviolet oven in order to cure and fully solidify the part. Finally, the model can be sanded down using an ultrafine sandpaper to produce a smooth surface finish. Stereolithography is commonly used for creating small to medium-sized concept models or prototypes for aerodynamic testing in wind tunnels, as well as parts with fine details such as those used in biomedical engineering.
Alright, so this is SLA. The next process is direct energy deposition. So direct energy deposition, it can actually deposit materials on existing structures. So it has been used a lot in some repairing functions or operations because it uses energy source, either energy laser or electron beam, as well as feedstock materials at the same nozzle there, and then gonna deposit the melted material or feedstock on the structure, existing structure there. So this is how it works, because the melted material will eventually solidify after the energy source is moved away, right? Different processes you can see. There's laser engineered, net shaping, laser solid forming, all the ABM, all others. Let's just have a general look at this direct energy deposition process. You can see here it not only have energy source, but also have the feedstock materials. mention some other processes within this category. The first one, the lens. Oops. Oh, this is actually a website. This is the repairing operation. All right, now let's look at the direct metal deposition. All right, so next one is electron beam.
Additive manufacturing offers greater freedom in design and allows for the creation of optimized parts that are not constrained by the limits of traditional manufacturing. RCAM EBM has the unique ability to tightly stack parts within the build in order to increase productivity. An optimized build file is sliced and loaded into the RCAM EBM system. Following this, metal powder is loaded into the machine. The build chamber is then closed and a vacuum is created to ensure a clean, controlled environment that allows for the processing of reactive material. Next, RCAM EBM's powder layering system evenly distributes a thin layer of powder on the build area. A powerful 6 kilowatt electron beam heats the powder bed to the optimal ambient temperature and then proceeds to melt the powder. First, contour melting and then hatch melting. The electron beam unit generating the beam contains no moving parts, allowing for extremely fast and accurate beam control. The build environment is kept hot, reaching temperatures exceeding 1000 degrees Celsius, resulting in no residual stresses and allowing for the processing of crack-prone materials. As each layer is completed, the build is lowered and a fresh layer of build powder is raked over it. This process repeats, growing the build one layer at a time. When the build is complete, the tank is extracted and the RCAM EBM machine is prepared for the next build.
All right, so direct energy deposition, it has multiple advantages that we saw in the video before. Because it actually combines multiple materials, different source of materials. You can use different materials in a 3D printing. So this is a very clear advantage compared to other processes, and also it can be combined with traditional manufacturing process, for example, machining, right? And commonly used material can be titanium, stainless steel, or other alloys, and also it can have a large work envelopes compared to process that requires the powder bed. Usually that kind of workspace is very limited because of powder and also motors, so those kind of things. But for this process, it can have a larger work envelope. And some of the drawback is that because it's the deposition process, so there's usually has a lower accuracy and also surface quality, because all the reason we mentioned before, and so it's better to make less complex parts with compared to SLS and SLM. So the applications were particularly turbine engine repairing or some of the making some of the parts in in the automotive or aerospace industries. Then the last process we're going to talk about is laminated object manufacturing. So this process is basically we're using sheets, right? Sheet materials. We first put one sheet of the material on the platform, and then when I start between the two different sheets, between the two sheets, we're gonna have an adhesive extruder head, and then to deposit some of the bonding materials. So that sheets can be bonded. And then I'm gonna use a laser beam to to cut the shape of the material for that layer. And so this is how a start have this kind of bonding of the of the layer by layer. Then after that, we're gonna put another add another material sheet and then repeat the process again. So this is how this process works, and then make the part. And with this process, usually it's a little bit lower cost compared to other high cost machines, and both the metal and the paper can be used in the 3D printing. Then the drawback is that the resolution is determined by the sheet thickness. So basically, that's a layer thickness, and because it has to be a sheet, and making this it's a lot of time it's much larger than other materials. Other will be the microns. This maybe many times of the layer thickness than the other materials. All right, so that's all the processes. So this slide is a very good summary of all the common additive manufacturing processes. It laid out the methods, materials, applications, benefits, drawbacks, and resolution ranges. So I suggest you to go back and analyze this diagram or this figure, and look at have comparison of all these processes. For example, comparing all these resolution ranges, you can see stereolithography actually have a best resolution, while fused deposition process might have a higher ranges of those. And same with application. You can see what application it can be used for different processes. Sometimes it depends on the material, sometimes it depends on the accuracy, sometimes it might depends on the power of the machine itself. So so go back and read this chart, finish some of the assignments related to this lecture. All right, so that's all for today. So next lecture, we're going to talk about the materials that is used in additive manufacturing.